Hi everyone, welcome to my YouTube channel. Today we will be discussing about stationary states. So Schrodinger equation in 3D is given by this equation 1, I h cut del psi by del t minus h cut square by 2m del square psi plus v psi. Here we are considering that the particle is in a time independent scalar potential. So instead of Vrt, we are just writing Vr because V is independent of time. We shall solve this partial differential equation by the method of separation of variables. Let's say psi is phi r chi t, where phi is only function of r and chi is only function of t. Putting this in equation 1, that is in Schrodinger equation, we get this equation 2. Just put psi equals to phi chi in equation 1 and you will get equation 2. Now dividing equation 2 by phi into chi, we get this equation 3. Here we can see the first term is only dependent on the variable t and the second term only dependent on the variable r. So to satisfy this equation, they must be equal to a constant, and I am considering the constant as h cut omega. So the first part is I h cut by chi t d chi by dt equals to h cut omega, and just then solving it we get chi equals to a e to the power minus I omega t, where a is a constant, and the second term gives minus h cut square by 2m del square phi plus v phi equals to h cut omega phi. This equation only dependent on the variable r. Now according to the function Vr, we can solve it depending upon the problem, and we can get phi r. So total wave function is phi r into chi, and chi is a to the power minus I omega t. So we are getting phi e to the power minus I omega t, where the constant is absorbed by the function phi r. The function of this form is known as the stationary solution of Schrodinger equation. This is called so because the probability density is independent of time. This kind of solution has well defined energy which is h cut omega. Hence these are called energy eigenstates. This kind of solutions are only possible because the Hamiltonian is explicitly time independent, that is the potential doesn't explicitly depend on time. If we put equation 6, this equation psi equals to phi to the power minus I omega t in equation 1, that is this 3D Schrodinger equation, we will get this equation minus h cut square by 2m del square plus v into phi equals to e phi, where we are writing e equals to h cut omega. And the term in the bracket is h, where h is a differential operator which is known as Hamiltonian operator, which is given by h equals to minus h cut square by 2m del square plus v as a function of r. And from classical mechanics we know that Hamiltonian is the total energy of the system. That's why the Hamiltonian operator acts on the wave function phi r and giving its energy E. Equation 7 is the eigenvalue equation of the operator H. The allowed energies of the system are the eigenvalues of H. Equation 7 is the eigenvalue equation. This equation is the eigenvalue equation. So let's say h phi n is En phi n. So psi is, we know that psi is phi into e to the power minus I omega t. So here we are writing psi n as phi n e to the power minus I omega n t, where omega n is En by h cut. So putting omega n's value in this equation, we get phi n e to the power minus I En t by h cut. As Schrodinger equation is linear and homogeneous, so any linear combinations of solution is also a solution to that equation. So the general solution is given by psi equals to Cn psi n, and we know psi n is given by phi n e to the power minus I En t by h cut, where Cn is some constant of expansion. So at t equals to 0, the wave function is given by psi r0 equals to Cn phi n r. Usually this constant Cn is a complex number. So in these kinds of problem, determining time evolution of wave function is very easy. You just have to write the wave function at t equals to 0, that is psi r0, in terms of the energy eigenstate phi n. That is, you are decomposing the wave function at t equals to 0 in terms of the eigenstates of energy phi n r, and then just multiply it with the exponential term e to the power minus I En t by h cut, where En is the energy corresponding to the particular energy eigenstate, and that's all. You get the time evolution of the wave function. So thank you so much for watching this video. If you liked my video, please subscribe my channel and share it with those who are interested in quantum mechanics. See you in the next lecture.